transfer into and out of the brain. If you look at this device in a nutshell, it's really just sampling voltages in the brain and sending them over radio. But if you zoom out and look at the system from end to end, what you actually see is that we're connecting your brain, or a biological neural net, to a machine learning model, or a silicon neural net on the right-hand side. And I actually think this is really elegant, because the machine learning model on the right-hand side is in fact inspired by neurons on the left-hand side. And so in some sense, we're really extending the fundamental substrate of the brain. For the first time, we're able to do this in a mass market product. That's a very, very special piece of hardware. So these are some of the first implants that we ever built. There are electrodes that were made with our in-house lithography tools. We have custom ASICs that we also designed in-house. And this was really a platform for us to develop the technology that allows us to sense micro-level volts in the brain across thousands of channels simultaneously. We learned a lot from this, but as you'll notice in the right two images, there are USB-C connectors on these devices. These were not really the most implantable implants. This next set of images are the wireless implants. And there was a complete evolution that we went through to add the battery, the antenna, the radio, and to make it actually fully implantable. Once it's implanted, it's completely invisible. It's very compact, it's modular, and it's a general platform that you can use in many places in the brain. Going from that top row to the bottom row is very challenging. The implant you see on the bottom right here is in fact the device that we have working in 7 participants today, and it's augmenting their brain every day and restoring their autonomy. But getting to that point involved a huge number of formidable engineering challenges. We first had to make a hermetic enclosure, passing 1,000 separate conductors through the enclosure of the device. We had to figure out how to make charging seamless and work with very tight thermal constraints in a very, very small area. And then we also had to scale up our testing infrastructure so that we could support large-scale manufacturing and very safe devices and have confidence in our iteration cycle. So what's next? We're going to be increasing our manufacturing so that we don't just produce, a small number of implants per year, but thousands and then eventually millions of implants per year. We're also going to be increasing channel count. More channels means more neurons are sensed, which means more capabilities. In some sense, we often think a lot about the Moore's law of neurons that we're interacting with. And in the same way that Moore's law propelled forward many subsequent revolutions in computing, we think that sensing more and more neurons will also completely redefine how we interact with computers and reality at large.